This is the simulated turning DOE. Now you can open up the file that I created, simulated turning DOE.mpj, and we'll go through how we used a 16 run, up to 10 factors, and up to 5 combined effects, interactions to design this, or you can design your own. But let's go through and see if we can recreate this experiment that's in here. And this is the completed one. The cost per pound of material removed has been calculated for all of the experimental run conditions using the simulator. Let's go ahead and generate this layout so you can see how we did this. So stat DOE factorial, we're going to create a factorial design. And when you do that, because we use the full layout and we have a number of unused columns, you have to create it the same way. So in this particular case, we're going to have up to 10 factors. All right, the designs that are available to us, it would be a 16 run. We're only going to have one data point per run, as you can see here. There's only one data point per run, so one replicate. I'm going to say OK. And the factors, when we go to put these in, all right, the first one that we assign to column A, and we assign speed to that one. All right, it is numeric. And the low setting is 100. Tab over, and the high setting is 150. All right, column B. All right, column B is unused, so we're going to call that U1, unused 1, and we'll just leave it as minus and plus and call it good. Okay, factor C. And column C, that's going to be feed. It's numeric, and the feed settings are 0.01. We're going to tab over, and 0.025. In column D, that's the one we put in for depth. And the depth of cut, the low setting is 0.035. And the high setting is 0.065. Column E, that is going to be U2. All right, that's unused, number 2. Then we have column F, and that is going to be unused, number 3. We have column G, that is going to be unused, number 4. Now, when we do our analysis, these are all these U names are all going to get combined immediately. They'll get dumped into, when we do our pooling, all of those will get pooled, plus whatever variables don't seem to have any kind of an influence. All right, now column H. Column H is our coolant quantity. So we're going to call this cool QTY. And it is numeric, and the low setting for the coolant quantity is 0.01, and the high setting for that is 0.05. All right, we'll tab over, and our column I is their column J, and our column J is their K. So that's a little confusing. Sorry about that. All right, so HI, they don't use I, they go right to J. It's okay, we know what it is. And this is our coolant cost. I'll call that cool dollars. All right, so the low setting for the cool dollars is 0.1, 10 cents, and 0.2, 20 cents. And last but not least is K. All right, and that is actually RJ, but that's all right. All right, and so that's the tool, and this is the tool, and this is actually text. So we're going to just say that's text, and we have tool number 2 and tool number 3. So this is going to be T2, and we'll tab over, and this is going to be tool number 3. All right, so that's how we set the factors. Options, of course, we are going to not randomize the runs. We're going to store it in a spreadsheet. We'll say okay to that. The results, we're just going to get, we can get a summary table. Let's just say no results for now. We don't need a summary table. We'll say okay to that, and we can then go ahead and generate the design. All right, so it puts it in a separate spreadsheet, worksheet for us, and you can see here is the design. It's all laid out. And then you would actually then put in the response, and this would be our cost, okay, per pound, our cost per pound. All right, but let's go ahead and we'll go up to Big Blue Eye. We'll go left of the Big Blue Eye, that's the graph folder, left one more time, that's the worksheet folder, and let's actually grab worksheet number 1. And this is our worksheet that has all of the data in. All the cost per pound data is already in there. So now we can go ahead and do this analysis and find out what the best settings are going to be. All right, so let's go ahead and see if we can do that. So it's going to be stat, DOE, factorial, and now we're actually going to analyze this factorial design. And cost per pound, all right, the terms. All right, so what we can do before we even get too carried away is we can just leave all those columns that have the U's in them actually out of it because we're not going to study those. So we have speed, feed, depth of cut, coolant quantity, tooling cost, cooling cost, and the tool. So it's 1, 2, 3, 4, 5, 6 factors. And then from the standpoint of our, we have the A times C, we have the A times D, and we have the C times D combined effect. So these are all the things that we're planning on studying. All right, and all the unused columns, we just left them out. All right, so U1, 2, 3, 4, those we left out. All right, so now we're ready to conduct our experiment, do the analysis, say okay. All right, the results, let's see, I'll click graphs first. Graphs, Pareto, 0.05, say okay to that. The results, make sure we have all of our factors in here. Coefficients in an ANOVA table, we want to see that. So we've got all of our variables and the 3 combined effects. So let's go ahead and say OK. And then we want to say OK. All right, and what we're seeing here is that really a lot of stuff is important here, but probably some of these are not as significant as others. We've got some real strong factors, C and D and A, the CD combined effect, and then we start kind of dropping off H and AC, but K, AD, and J, we're probably going to want to be getting rid of those. So K is the tool. That probably didn't, seems like that's amazing. That doesn't really matter. The AD combined effect and J, the coolant cost, doesn't seem to make much difference. So let's take a look at the session window. And we'll come up here and we see that we've got significant main effects and two-way interactions. Well, look at this, great 98% model. But remember, when we look at these regression models, it doesn't really mean anything if we have some t-statistics that have a absolute value that is less than or equal to 1. All right, so we see that the coolant dollars, that needs to be taken out of there. And then if we look at what we started with, we had 6 factors plus 3, so it's 9 total elements that we were studying. We should have about 4 or 5 of those guys left over when we're done. So we need to combine some effects here. So what we're going to do is we're going to take out the smallest of the effects. And you can see that the interaction effects, the one that we're probably going to keep is the feed depth combined effect. And then we have, let's see, we have 1, 2, 3, 4. Even the coolant quantity isn't that strong, but we'll probably keep that one. And when we get to the final ANOVA, as long as we've got about 4 or 5 factors left, and it appears that, make some notes on this. Let's see. So speed, that looks like something that we want to keep. We'll go back to our, let's go back to our graphs here. Big blue eye, go back to the graph. All right, so it looks like we want to keep the speed, all right, which is, we want to keep the feed, which is factor C. We want to keep D, which is the depth of cut. We want to keep A, which is the speed. We want to keep the C times D combined effect. H is the coolant quantity. So that would be 1, 2, 3, 4, 5 of those, and then we'd be getting rid of 1, 2, 3, 4. So we can probably lose the AC combined effect. Okay, so we're going to keep the coolant quantity, which is H, we'll keep that. And then we're going to get rid of everything else. So let's go ahead and do that. Edit a last dialog box, go to terms. All right, so we're going to keep the speed, we're going to keep the feed, we're going to keep the depth of cut, we're going to keep the coolant quantity. The coolant dollars, we're going to take that out of there. All right, the tool wasn't really important. All right, we want to keep the C times D combined effect. We're going to lose AC, we're going to lose AD, so we've got 1, 2, 3, 4, 5. We started with 9, want to have about 4 or 5 left over. We'll say OK. And then we can say OK. We'll just double check the results here to make sure that that's correct, and it is. We'll say OK. Generate our analysis. And you can see that H is just on the hairy edge of being significant at a p-value of 0.05, which would give us a 95% confidence. So that's just barely making it. But everything else is really strong here. So the speed, the feed, the depth, and the coolant, and the C times D combined effect. You know, the coolant quantity is really kind of iffy, but we're not going to get rid of it now. We've got it in the model. Let's take a look at our session window. Up to big blue eye, go over to the session window. And we can scroll up here. And let's take a look. Main effects, significant, at 99.9 some number, % confidence. Interactions at a 99% confidence, p-value 0.01. All right, R-squared adjusted, 93%, very strong model. And we can see that the coolant quantity has a p-value of 0.05. And our feed times depth of cut is a 99%, and everything else is very strong. Okay, so this is all good stuff. We have our coefficients, okay, the constant plus the coefficients. So you actually have the model here for the regression model. That would be the equation, and that'll be used by the response optimizer. All right, and let's go ahead and graph some of these. And we'll go to stat, DOE, factorial plots, and main effects and interaction. We'll set up the main effects, and feed, speed, depth, coolant quantity. We're going to get rid of the tool. I mean, we could leave it in there, but we didn't keep it. Speed, feed, depth of cut, and coolant quantity. That's our main effects. The interaction is going to be our C times D. So C times D, feed times depth of cut. And go ahead and say OK. And I'll make this one big so you can all see it. All right, so what we're looking at is the combined effect of the depth of cut and the feed rate. So what it's telling us is we want to go fast, we want to feed it fast, and we want to take a lot of material off. So we are looking at a feed rate of 0.025. We are looking at a depth of cut of 0.065. And if we look at the other factors, and we'll show the graphs folder, go to the main effects plot, make that big. All right, so from a speed standpoint, we want to be going at 150. All right, from a depth of cut 0.065, which is what we had. The coolant quantity, it's really not that strong, but it is suggesting to use a coolant quantity of 0.01. All right, and it really didn't matter which tool that we used, and it really didn't matter the cost of the coolant, okay, as long as we had these variables set here. So let's see if we can get a prediction using the response optimizer. ANOVA, DOE factorial, and we'll go to the response optimizer. Cost per pound of material removed, we're going to set that up. We want to minimize it. Let's see if we can hit a target that we have to put in here. No, I don't know. Let's see if we can put it at 0.5. Let's say OK. And OK. All right, so it's saying that we can get down to 68 cents as a cost per pound of material removed if we're running that 150, 0.025, 0.065, and 0.01 for our coolant cost. All right, so that's what it's telling us. And what you can now do is just go back to the simulator, and you can plug these numbers in, and you can see what the value comes out to be. Now, you can play around a little bit with the coolant cost and the tool to actually see if when you change those, if it really matters very much. And it's really not going to make much difference. You may see the calculated value change slightly, but from a statistics standpoint, they weren't considered to be significant, so you should be able to choose the lowest cost settings. And let's see, where's my simulator? So the lowest cost setting for the tool between T2 and T3, T2 was the least expensive tool at $20, and T3 cost $30. So you could go with the T2 tool, and the lowest cost setting for the coolant would be 0.1. So go ahead and go with those as the lowest cost settings for the non-significant factors, and you should be able to get a cost per pound of material removed that's somewhere around that 0.68, 0.7. So the desirability index is pretty high, 0.82 on a scale of up to 100% of 1. So, and desirability is all tied into what we put into the setup as to the target values that we were shooting for. So if we were to put 0.7 in there, we'd have a desirability index of about 1. So it's a cool statistic that doesn't really mean much. All right, so that's how we actually do this DOE. We do the analysis, and we had our unused columns. But remember, when we use these layouts, if we are picking columns so that we can study the combined effects, which we want to do, then unused columns, it's okay to have them. When we go to run our analysis, we just don't include them because they're unused. So they just get automatically put into, well, we automatically do it ourselves, but they get put into the unexplained right away. And then we get to do our analysis, and there you go. Now you can run a 3-level design on this. You can run other 2-level designs. You could decide to hold some variables fixed. but the thing is, it'll give you a chance to run and conduct some design experiments. You're not going to break anything. It's going to give you real data that you can use. I have used this model in actual machining when we were working on minimizing the cost per pound of material removed. And a couple of the variables in here, we were actually measuring, which was the tool life. And it's kind of hard to simulate the tool life, so we gave you some expected minimum tool lives in this. But the tool life, you actually use a microscope and a measurement device to do that. And you can actually come up with minimizing the cost per pound of material removed by doing that, along with all these other factors that are in this model. So anyway, I hope you have some fun with this. It's a great little exercise. You can design any experiment you want. So go for it, have some fun. And remember, if you need some help with anything or you want me to see what you've done, just send it to help@educatevirtually.com and we will pay attention to you, our students.